Okay, so anyway, if for those of you who are watching online, thanks for clicking onto the next video. Welcome back to my channel. The what happened in the video was they did this experiment where they wanted to see if yawning was contagious, and they've selected 50 people to participate. And each participant, basically, they just had to sit in a small, tiny little room, and they were just watched for a few minutes, and they wanted to see if they yawned while they were sitting in the room. But before they entered that room, one of the hosts, Carrie, she would either yawn in front of the person, okay, and they called that the seed yawn group, or she wouldn't do anything, she didn't yawn, and those people would be in the control group. And so they did that, and then they checked to see if the people in the seed yawn group were more likely to yawn versus those in the control group, and they recorded everything. And at the end of the experiment, they looked at their data. They said, hey, we had 50 people, and they said 2 out of 3 people were in the seed yawn group, and 1 out of 3 people were in the control group. And so, and they said, in the seed yawn group, 29% yawned, and in the control group, 25% yawned. So I kind of tried to back solve, and so these are the numbers that I figured out. So out of 50 people, if 2/3, which is around 34, okay, 34 were in the seed yawn group, and 16 were in the control group, and 10 out of 34 would produce a proportion of 29%, 0.294, and for the control group, 4 out of 16, that would produce 25%, okay? So our observed proportions were 29% and versus 25%, and they said, that difference of 4 percentage points, while not dramatic, because the sample size was so big, they said, yeah, it seems like this confirms the thing that yawning is contagious, and so that was their conclusion. Okay, it says so now one thing to note is that the people who were selected was not a random sample. Okay, and but who got assigned to be either in the control group or the treatment group, it was systematic. They said 2 out of 3 and 1 out of 3 would be every third person would be in the control group. But but the order of people who lined up, that could have been random, right? Like if something was just ever so slightly different, the order of people who lined up to participate might have been a little bit different, and they would have gotten it would have been different people who was assigned in each group. Okay, so we're going to say the treatments were randomly assigned. Okay, so this is how we could set up our hypothesis test, and we're going to say the proportion of people who yawn, the probability that someone yawns if they were in the seed group is going to be P seed, and the probability that someone yawns if they were in the control group is going to be P control. Okay. And the null hypothesis here is that yawning is not contagious, so the null hypothesis would be P seed minus P control. We're going to say that difference is 0. Okay, that's going to be the null hypothesis, that whether you're in the seed group or whether you're in the control group, it makes no difference. That difference is 0. Okay, the alternative hypothesis is that yawning is contagious. Receiving a seed yawn makes it more likely for the person to yawn, and so we're going to say the probability of yawning if you're in the seed group is greater than the probability of yawning if you're in the control group, so that difference is greater than 0. Okay, what we got was 10 out of 34 minus 4 out of 16, a difference of basically 4 percentage points, 4.4 percentage points. Okay, and we want to know, is that difference statistically significant? Now, one thing to note is that we can't do a Z proportion test, because to do the Z proportion test, the central limit theorem has to apply, and we need at least 10 yeses and 10 nos. Okay, in the seed yawn group, we have 10 people who yawned and 24 people, 34 minus 10, 24 people who didn't yawn. Okay, but in the control group, we have 4 people who yawned, okay? Only 4. So that's not over 10, so we don't have enough people who yawned in the control group. We got 12 people who didn't yawn, but only 4 who did. So that's not big enough, okay? But let's, so we're gonna go with a randomization test, and we have to think, okay, how are we gonna do this? With a randomization test, we wanna know what is possible if the null hypothesis were true, right? We wanna know what kind of values can we get if the null hypothesis were true. And so if the null hypothesis were true, then we're gonna say whether a person yawns or doesn't yawn is independent of whether the person gets a seed yawn or not. That is to say that getting the seed yawn or being in the control group has nothing to do with the person yawning, and that any kind of difference we observe is just a result of the random assignment of treatments, okay? Another way to think of this, and it feels a little weird saying this, but is to say that, you know, we had 50 people who were volunteered to be part of our experiment, and at the end of the day, 14 people yawned. And we're saying that if the null hypothesis were true, is that those 14 people who yawned, they were destined to yawn, whether they were in the control group or whether they were in the seed group. These people were going to just yawn no matter what, and it had nothing to do with whether they saw carry yawn in the seed group or not, okay? And so the fact that 29% yawned in one group and 25% yawned in the other group is just a result of just kind of random coincidence. And we're saying that, you know, random shuffling alone could have produced that difference of 4.4 percentage points, okay? The p-value in this context is the probability of observing what we got or something more extreme if the null hypothesis were true. And so we're saying if the null hypothesis were true, what we would expect is the difference between our two groups to have no difference in the proportion of those who yawned, okay? We observed a difference of 4 percentage points, a difference of 0.044. And so we want to know if we assume that two populations have the same proportion of yawners, what's the probability that by random assignment we could produce samples of data where that difference is 0.044 or something more unusual, okay? And so with a randomization test, we're going to try to simulate what kind of sampling distribution we could get if the null hypothesis were true, okay? The null hypothesis states that the random assignment of treatments is the only source of variation between the sample proportions. And so what we're going to do is we're going to simulate the idea that we have 50 people and 14 are destined to yawn. And what we're going to do is we're going to put them into two groups. Group A is going to have 34 people and Group B has 16 people. And we're going to just shuffle them into these two groups. And we're going to say, okay, how many people yawned in Group A and how many people yawned in Group B? And because we did the random assignment ourselves, we know that if there's a different proportion of yawners in Group A than Group B, we know that that difference is because of just the randomizing, right? Because we did the randomizing. There's no reason why Group A or Group B should be different other than the randomizing process, okay? We didn't do any kind of, we're just taking basically yes and no responses and just shuffling some over here and shuffling some over here. So when we get a difference from this group and the difference in this group, we know that difference is only because of the randomizing, okay? And we're going to just repeat this over and over and over again, and we want to know what kind of differences could we get just from randomizing, okay? And we want to know, is the difference of 0.044, is that unusual or not, okay? And if it turns out that, you know, you shuffle these things and getting a difference of 0.044 is unusual, then the fact that we did get a difference of 0.044 indicates to us that, you know what, this is not the result of randomness, that our null hypothesis is wrong, and getting the fact that we got 0.044 is because of something other than randomness, okay? On the other hand, if it turns out getting 0.044 is not unusual, okay, then we're going to say, yeah, maybe we got a difference of 0.044 just from the randomization process. So that we're going to say that, okay? Now, in order for us to use a randomization test, we need to have something called exchangeability. It must be reasonable to assume exchangeability. That's the big assumption. So basically, every time you do something in statistics, and this is true for the entire field, is you have to make some assumptions, because statistics is all about drawing conclusions from the data you have. And so you have to make some assumptions about your data. A lot of times your assumption is the data I have is representative of this bigger thing, okay? And oftentimes that's a reasonable assumption. Sometimes it's not a reasonable assumption, right? And so that's going to lead you to the wrong conclusion, all right? In our case, or for parametric tests, your assumption is the sampling distribution that's underlying the generating process. It can be modeled with a normal distribution, okay? And you take 100B and you prove like why that's a reasonable assumption, okay? In our case, we're going to say the assumption we're making is that the data we have has exchangeability. Exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely, and technically it means any permutation can be exchanged with another permutation of the data. So on a practical level, this means that exchangeability applies to experiments where random assignment has been used, okay? And the idea is this. Imagine you are going to run an experiment and you get like 50 volunteers who sign up, all right? And you say, all right, I need to put some of you into the control group and some of you into the treatment group. So how are you going to do this randomly? You'll probably go on your computer, you'll type in set seed 1, and then you'll do like sample, control versus treatment, this and that, and then you'll just hit enter and you'll get like these people go into control and these go into treatment, okay? But if you decided to do set seed 2, you're going to get a totally different set of assignments, right? Or if you did set seed 3. And all of those assignments are equally valid, okay? And so exchangeability says, yeah, who got assigned to which group, that's just random, and we could have just exchanged any random assignment with any other random assignment. So that applies to kind of random experiments. And it's sort of the Mythbusters one, again, how they lined up, the order in which participants lined up could have been exchanged with any other permutation of the order that they lined up, and that wouldn't have impacted the experiment at all. And so who got assigned to the control group and who got assigned to the treatment group, that's exchangeable, okay? If treatments or who's in which group is not assigned randomly, like an observational study, you're not going to suddenly be able to say like, oh, we're going to just change which, personal trait you has, right? So maybe you're doing like, people who with this particular, whatever, people of this gender versus that gender or something else or whatever, you can't just exchange those things. And so permutations aren't going to apply there. So you can't do exchangeability there, okay? But anyway, basically, if you do a random experiment with random assignment, exchangeability applies. All right, so this is how we might input our data into the computer. Here I'm going to create a vector of 50 values. I'm going to use a logical vector, true and false, because with a logical vector, you can do things like, what is the mean? And it will give you what proportion is true, yeah? So if you take a logical vector and you say, what's the mean of this logical vector? You get the proportion that's true. And so here I have a vector of length 50, and I have basically a total of 14 true values. I repeat true 10 times and true 4 times here, and a total of 36 false values, okay? And true is going to represent someone who yawned, false represents someone who didn't yawn. And so here I have the first 34, 10 who did yawn and 24 who didn't. Over here I have 4 who did and 12 who didn't for the 16. And so for the treatment group, we're going to put in the first 34, and for the control group we'll put the remaining 16. And I could say, what is the mean of treatment? 10 out of 34 gives me a proportion of 29.294. I could say, what's the mean of control? And I get 0.25, 4 out of 16, okay? And then I could say, hey, what's the difference between proportions? I do mean of treatment minus mean control. and that gives me the difference between proportions, a difference of 4.4 percentage points. So this is basically just the data that we have from the experiment. Okay, so far so good. What I want to do now is I want to do the randomization test. So what I'm going to do is I'm going to use sample, which basically takes our vector of 50 values, okay, and it just shuffles them up. and I mistyped and I wrote shuffle here, but it should be sample, okay? Python has shuffle, random.shuffle, but basically you just take your vector and you're going to just shuffle the order, and you can do sample, okay? And so only you'll still have 14 true and 36 false, but just the order in which they are will change. So here I do set seed 1. I get I'm going to sample my values. I'll randomize them. And so now these 34 values here for randomized end up in group A. This is just a result of the random process. I take the remaining 16 and I put them into group B. What true-false values end up in group B is just a result of the randomization process. When I say what proportion of group A is true, I get 0.294. And what proportion of group B is true, I get 0.25. So my difference that I got randomized also ends up being 0.044, which is exactly the same difference we got from the Mythbusters experiment. So far it feels like, oh, well, this could have been the result of just randomness, right? But this could have also just been random coincidence, right? So if we did a different random shuffling, we might very well get a different result, okay? So we'll try this again. So I do set seed 5 here. I just shuffle that vector of 50 people. 14 of them are going to yawn. And I shuffle them up and I say, all right, put 34 into group A, 16 into group B. I have to do 34 and 16 because those are the group sizes I have in my original data, okay? So you don't want to just suddenly just change it up and do like 25 and 25 or something like that, okay? You want to kind of mimic what group sizes you have in your original data. So I had 34 and 16, so I put 34 into group A, 16 in group B. Again, who ends up in group A is just purely a result of just this randomizing sample, okay? And here I get 23.5% in group A yawned and 37.5% in group B yawned. So here in group B, I get a greater proportion who yawned, and I get a difference of negative 0.139, so almost negative 14, 14 percentage points there, okay? So this is the randomization test. We're going to just randomize this and do this, repeat this process like 10,000 times, okay? So I'm going to say, and each time in my loop, I do a for loop. I'm going to say just shuffle that vector of 50 values. That's going to be my randomized thing. Put the first 34 into group A. Put the remaining 16 into group B. Calculate the proportion of group A. Calculate the proportion in group B by using mean. Take the difference between those two proportions and store that away in differences. Okay, and so we do this, and what do we get? Okay, the mean difference is right around 0, okay, which is what we would expect. We would expect the mean difference to be right around 0. Our median difference is 0.044, okay, and sometimes the difference between group A and group B is as big as 0.411. Sometimes it's as negative as 0.599, okay, so we get kind of a wide range of possible values between our group differences, okay. And we can say, okay, well, how often? So what we observed was a difference between, 10 out of 34 and 4 out of 16, a difference of 4.4 percentage points. And we could say, well, how often would you get a difference of 4.4 percentage points just from random chance? And so I could say, okay, take a look at all of the differences that I generated. I got 10,000 of them. How many of those differences are greater than or equal to 0.04411765? Okay, and it says, hey, that happened, over 50% of the time. So I did this 10,000 times, and 5,070 times I got a difference of 0.044 or something bigger. All right. So when Mythbusters says, yeah, the difference isn't dramatic, 29 versus 25%, the difference isn't dramatic, but our sample is big enough. I think it confirms. our answers is no, the difference isn't dramatic, and in fact, you can get a difference like this from random chance with a probability of over 50%, okay? So, so it's not, we would not be convinced, right? We look at our data and we're saying, we are not convinced by this kind of difference. So our empirical p-value based on our randomization is 50%, and we're saying, this randomization process has a high probability of producing the data. I haven't given you view quiz answers yet, have I? Okay. What are the last two view quiz answers? Okay, I'll give you the last two. E and C. E as in elephant, C as in cat. E and C. So based on our results of the randomization test, it says, this data that Mythbusters pulled out could have very well been the result of randomness, okay? And it would not be convincing to us that the seed yawn actually makes a difference, because all we've shown is that randomness could have created this difference. So we're not going to say that the data, what we will say is the data does not provide reason to believe that getting a seed yawn makes a person more likely to yawn, okay? At the same time, we cannot conclusively say that yawning is not contagious, okay? It's just our data doesn't provide evidence that it is contagious, okay? And it's possible that the seed yawn increases the probability of yawn, but maybe we didn't collect enough data, or maybe for whatever reason we happen to get data that doesn't look this way, okay? We could have also asked this question: does seeing someone yawn have any effect, positive or negative, on a person yawning, right? So seeing someone yawn may make some people more likely to yawn, and seeing someone yawn might actually make some people less likely to yawn. Like maybe they go, ooh, they're yawning and I don't want to be embarrassed and I don't want to yawn too, or I don't know, whatever, right? We're not trying to explain why. We just want to know, hey, is there any kind of difference, positive or negative? And so in that case, you would take the absolute value of the difference. We would be interested if this difference is 0.044 or something more positive, or negative 0.044 or something more negative. And when you do that, you get 1. We get a p-value of 1, okay? Which feels weird. Like, is that even possible? And the answer is yes, it is possible. And let me show you, okay? So our data, we got 10. There's a total of 14 people who yawn, right? 14 people who yawn. And so you have to split those between two groups. So one group has 34, the other group has 16. So we could do 10 in one group and 4 in the other, and you can calculate, okay, what's the difference in proportions, and we get 0.044. That is our difference that we observed, okay? You could also split it 9 and 15, okay? If you have 14 to do, and in that case, you would get a difference of negative 0.047, okay? Negative 0.047. If you have 14 people, you could try splitting it with 8 and 6, 8 and 6, 8 and 30, 8 in this group and 6 in the other group, okay? And when you do that, you get a difference of negative 0.139, okay? And, I think we would all agree that if I split it any more, right, if I did 7 and 7, it would just drive this to be even more negative, okay? I could go the other way, okay, and I could do 11 and 3, and the difference we get there is positive 0.136, okay? And if I try any other kind of split here, so if instead of 11 out of 34, if I did 12 out of 34 minus 2 out of 16, our differences just get even bigger and bigger, right? 13 and 1, 0.319, and then finally 14 and 0, okay? And this is the greatest possible difference. So everything just kind of drives it more extreme in that direction, okay? The other one, what do we say? Again, we have to do 8 and 6, 8 out of 6 out of 16, and if I do it anything, anything less than the 7 and 7, we get something more negative, 6 and 8, even more negative, 5 and 9, okay? And so you can see just everything just gets either more positive or more negative. And so when you look at the results, the most balanced possible choice that we have between the proportion who's going to yawn in one group and the proportion in the other group, the smallest possible difference we can generate is 0.044, okay? So when Mythbusters says the difference isn't dramatic between 29% and 25%, you say, yeah, it's not dramatic. And in fact, it is literally impossible to get a smaller difference between the two proportions. There's no possible way to split 14 people who are going to yawn into two groups where you're going to get a difference smaller than 4.4 percentage points, just the way the numbers are, okay? Because some have to end, you're either going to have, 9 and 5, 3 and 10, or 3 and 11, 10 and 4, or something like that. There's no possible way to split 14 people into two groups where you're going to get a difference smaller than 0.044. So yeah, the difference isn't dramatic, and in fact, it is the smallest possible difference we could possibly see. So all to say, we are not convinced that this data shows that yawning is contagious. Perhaps we could do another experiment and it is actually contagious. I don't know. Just anecdotally, it feels like it is, but if you wanted to try to show and demonstrate it, this is not the experiment that does it. Okay. All right. So we will we'll wrap things up here, and that's it for today's lecture. Have a great rest of your Monday. Hopefully, week 9 is going well, and we'll see you Wednesday.